Dear students, Assalamu alaikum. In our previous video, we studied IR spectroscopy, basic principles, vibrational modes and different vibrational energy levels, and then we studied that what are IR active and inactive vibrational modes. In this video, we will study Hooke's law and different factors that affect vibrational frequency. So first, let us see that what is Hooke's law. Stretching vibrational according to this law, stretching vibrational frequency increases as number 1 the strength of bond increases, number 2 the electronegativity difference between bond increases, that is force constant between bond increases, and number 3 the mass of atom decreases. So we take examples one by one. Like here we have strength of bond increases. If we look at the strength of bond, there is carbon-carbon single bond. The strength increases in carbon-carbon double bond and then further increases in triple bond. So in this case, the vibrational frequency of the carbon-carbon single bond is less than double bond and it is less than the triple bond. If we look at the electronegativity difference or force constant between bonds, the carbon-carbon double bond, here we have zero electronegativity difference, but we have electronegativity difference in carbon nitrogen and also the greater in carbon and oxygen. Therefore, the for frequency increases gradually. Similarly, here if we look at another example, the difference between CH, then NH and OH increases. So the electronegativity difference increases, and in this way the absorption frequency of these bond increases. The third one is the mass of atom decreases. Here we have example like hydrogen iodide have less absorption frequency than hydrogen bromide, and hydrogen bromide have less absorption frequency than hydrogen chloride. So the mass of the atom, this iodine, bromine and chlorine, that is going to decrease, then absorption frequency is increased because the other atom is hydrogen, which is same in all three bonds. So the reason behind this is, here we are going to explain the reason. Like here, if we look at the stretching vibrational frequencies like carbon and oxygen single bond, so the less energy is required for the stretching between carbon and oxygen, whereas the more energy will be required when we are going to stretch this carbon oxygen double bond, and therefore this bond requires more energy and thus more frequency for stretching than this one. Now we are going to take example of the mass. Here we have hydrogen chloride and this is hydrogen bromide. So here mass is greater. So in this case, if we consider that this hydrogen is present here and it is stretched with the spring, and here we have a weight of the bromine, so it will be stretched more and we require less energy to stretch this. But in this case, here we have chlorine which has less mass and we have required more energy to stretch this atom at this position. So in this case the mass is less, thus we need more energy to stretch this atom. Thus we can say that the frequency is required more and the absorption frequency of the bond increases. The last example that we studied, that electronegativity difference. So for stretching this bond, hydrogen oxygen, it has more electronegativity difference, so the bond will be stronger. So we need more energy to require this stretching. But in this case, here we have hydrogen and nitrogen as compared to this hydrogen oxygen. This the electronegativity difference is less, therefore the less amount of energy is required to stretch this bond because the bond is less stronger, or electronegativity difference is less than the electronegativity difference between hydrogen and oxygen. So more energy means more frequency or high frequency, which means higher wave number but lower in wavelength. Now we can take an example of IR spectrum. So if we look at the IR spectrum, we should know that how it can be read. So on x-axis, the wave number is shown, which is from 400 to or 500 to 4000 per centimeter, which represents frequency wave number. So this wave number increases in this direction, so frequency also increases in this direction. So higher frequency, higher wave number and higher energy, but the wavelength is in opposite direction. So I am going to show here that it is from 2.5 micrometer to 16 micrometer in this direction, which is IR mid region. And in this case, the y-axis represent percentage transmitters from 0 to 100%. And if we look at the absorption will be like this from 0 to 100%. So at the bottom there will be 100% absorption, or it means that the 0% transmitter. So these IR peaks will be like this. So here we will represent this region. These are the peaks that represents the maximum absorption. So in this way we read the IR spectrum. Now moving on to the factors that affect IR absorption frequency. So what are these factors? So these factors are: number one, the electronic effect. Electronic effect can be further divided into two different effects. Number one is the resonating effect and number two is the inductive effect. So both these affect the absorption frequency of the vibrational frequency of our compounds. So electrons shifting due to inductive effect or resonating effect may shift the absorption frequencies. For example, if we consider the carbonyl system, here we can observe that this electron, this double bond between carbon and oxygen, can be represented like this. If these pi electron are shifted here or moves here, so in this way we have a resonating structure will be like this. So now this double bond has like this character and this. So any factor that tend to increase the contribution of single bond will result in lowering of the stretching vibrational frequency. For example, conjugation. So any factor that tend to increase the contribution of single bond. So when the single bond character will increase or the strength of single bond character will increase, the frequent absorption frequency, so absorption frequency will be lowered down. We are going like here we have a conjugation or resonating system which lower down the which increase the single bond character, then double bond character. So here we have shown that this partial double bond. So conjugation due to alpha beta unsaturation or aromatic ring reduces the absorption frequency. Like here we have a carbonyl system and it is conjugated, or it is attached with some other conjugation system or aromatic system, the absorption frequency will be decreased. Here we are going to take example. Like here we have only C double bond O. So this carbonyl system has stretching base absorption is, or base frequency is 1715 per centimeter, which is the absorption frequency or baseline absorption frequency for this bond. Now if we have a conjugation with this carbonyl system, so the stretching frequency of this carbonyl system CO bond will be lowered down or decreased, because this resonating structure produces electron donating effect which lowers down, so the electron will be shifted here, so which lowers down the absorption frequency of this carbonyl system. And again if we have a resonating structure here, like here we have a aromatic ring, it also increases the single bond character of this carbonyl system, and again the absorption frequency will be lowered down or decreased. Here we have another example which is in alkenes, like here C double bond C stretching, which has maximum absorption frequency at 1650 per centimeter. If this C double bond C or this double bond is now in connection with conjugation, so now we have a conjugation system. So the this bond will be can be shifted here, and this double bond or the electrons by electron can be shifted here, so it will increase the single bond character as compared to double bond character of this CC stretching. So in this case the absorption frequency decreased down, so it will be from 1650 per centimeter to 1610 per centimeter. Here are some other examples, like here we have vibrational stretching of carbonyl system at 1715 per centimeter, and now here we have a resonating structure. So in this case it will be lowered down to 1690 per centimeter. And if we look at this stretching, carbon-carbon stretching, it is in simple compounds or where we have no conjugation, it will be 1650. But here now it is in conjugation with carbonyl system. So if you look at the both frequencies, both bonds, so it is decreased from 1715 to 1690, and here it is decreased from 1650 to 1610. So the absorption frequency of this bond also decreases because it is now in conjugation with this carbonyl system. So both produces effect on each other. So though both of these bond produces effect of each other, and the frequency of both of these bond decreases. So any substituent that enhance the single bond character will lower down the absorption frequency. Now we know that we have electron donating and withdrawing effect. So we can assume that we have these electron donating resonating effect, which can be represented with plus m, or electron withdrawing resonating effect with minus m. So these two are the resonating effects, and electron donating inductive effect plus I, and an electron withdrawing inductive effect that is represented with minus I. So we can represent these symbols to represent our compounds that what kind of effect is now going to produce any kind of the atom. So these two are the resonating effects, donating and withdrawing, and same is the case in inductive effect. So inductive, donating inductive effect and withdrawing inductive effect. So these are the four different effects which can be responsible. So now we are going to take another example. Now we are going to take example of the inductive effect. Before we considered the resonating effect. So in this case we have 1730 per centimeter. So increase single bond character here. This methyl group or alkyl group, due to hyperconjugation, it has electron donating inductive effect. So it is represented with plus I. So it has electron donating inductive effect, due to which it enhances the single bond character of this bond. So this reason the absorption frequency is decreased or lowered down. So due to alkyl group, which produces electron donating inductive effect, not resonating. Now it is producing inductive effect, which is electron donating inductive effect, and it is due to hyperconjugation, so it lowers down the frequency. But in this case here we have another example where the absorption frequency is going to increase from this one, so 1725 per centimeter. So why this absorption frequency increases? Because of this halogen atom attached to this methyl bond or alkyl group. So this chlorine, halogens have more electron withdrawing inductive effect. So halogens have more electron withdrawing inductive effect. So due to this negative I, or more electron withdrawing inductive effect, this double bond character is going to increase, and that's why the absorption frequency is going to increase as compared to this C double bond O. So the halogens are important because they have more electron. So here we are going to take some other examples, like here again this represents the electron resonating inductive effect. But before going to this, I am going to show you this one. Sometimes inductive effect has more impact than resonating effect, as in case of halogens. So we are going to study halogens, that what is the effect of halogens. Here we have 1715 per centimeter, but in this case here again this, due to this lone pair, it will shift these electrons here and it will be here, so it is the resonating effect. So this resonating effect lowers down the absorption frequency. So here resonating effect has greater impact. But in this case where we have methyl chloride, this chlorine has lone pairs and these lone pair causes resonating effect, electron donating resonating effect. But this resonating effect is nullified or decreased due to electron withdrawing inductive effect of this chlorine. So here inductive effect is more influenced as compared to resonating effect. So this inductive effect is greater than the resonating effect, therefore the vibrational frequency going to increase. And here we have shown the resonating donating effect and resonating donating effect and resonating withdrawing effect. So this carbonyl system, if we look at this carbonyl system again, it has 1715 per centimeter, and this oxygen has electron donating resonating effect. So this resonating effect causes this single bond character and the absorption frequency will be decreased. But in this case this nitro group has electron withdrawing effect. So electron withdrawing effect withdraw these electrons, and in this way, so this double bond character will going to increase and it will enhance the absorption frequency. So we have discussed the electron resonating and inductive effect. In our next video we will study the effect of hydrogen bonding and angle strain. So thanks for watching my video today.